All right, so today we're going to talk about polynomial functions. So what is a polynomial function? Here you can see written out is kind of the textbook definition of what a polynomial is, but more often we see it as something like this. We have a sum or difference of a number of terms. Those terms have a coefficient, which I'm using A, B, C here. They could be anything. They usually are whole numbers, but occasionally you'll see fractions and decimals. You will see this particular polynomial is in standard form. You can see that the exponents go from greatest to least as we go left to right. You'll notice that all of our exponents are whole number, whole positive number exponents, and that's just some of the key things that let us know that we're dealing with polynomials. We've dealt with a lot of polynomials in our lives. Linear functions are polynomials. They are first degree polynomials. Quadratics are second degree polynomials, and so forth. The degree refers to the highest exponent that we have. Effectively, that exponent dominates the others. So the degree of a polynomial, it will be identified as the greatest exponent of all the terms. Basically, the largest exponent has the biggest impact on the way our graphs look and behave. So we use this idea of a degree to identify what type of polynomial we're dealing with. We will also use something called the leading coefficient test. This takes into account both the degree and a leading coefficient, but a leading coefficient test describes the end behavior as a function. It describes the end behavior of a function. It will behave one of four ways. When we talk about end behavior, we really think about as x gets extremely large and negative, or as x gets extremely large and positive. What does the graph do? Now, polynomials inevitably will either go up or down as x gets extremely large in the positive or negative direction. Now, I'm realizing that I kind of wrote in a tough spot here, so I'm going to do some erasing of that notation. We'll come back to that in a little bit. Now, what we need to know about this leading coefficient test is the polynomial, does it have an even degree or does it have an odd degree? If our polynomial has an even degree, it would behave something like a quadratic, that U-shaped parabola that we've seen before. So if the leading coefficient, the graph will rise in both directions, both to the right and to the left of our graph. Similarly, if the polynomial has an even degree and the leading coefficient is negative, our graph will fall in both directions. With odd degree polynomials, we're going to end up going one up and one down. They won't match like the even degree polynomials did. If the leading coefficient is positive, our graph would fall to the left and rise to the right. And the opposite will be true if that leading coefficient is negative. It will rise to the left and fall to the right. So we have a few different situations where this comes up here. We're just going to look at these graphs. Effectively, these graphs show us that we don't really care what goes on kind of in the middle of our graph, or really what's going on in this dotted line area. We're going to cover that with like x-intercepts and relative maxes and mins. But what end behavior cares about, it really cares about where do these arrows go? Do they rise or do they fall as we go to the left or the right? In this case, we could see that the graph on the left here has positive lead coefficient and odd degree behavior because it falls to the left and rises to the right. This graph on the right here would have negative leading coefficient, negative LC, and odd degree. We know with odd degree polynomials, the end behavior end in opposite directions. One's up and one is down as we get extremely to the right or to the left. So both of these graphs that you see have odd degrees. As far as the leading coefficient, the direction that we end in to the right, here we can see we go negative, so we have a negative lead coefficient. Here we can see we go positive, so we'll have a positive lead coefficient. The end behavior in the positive x direction tells us all we need to know about the leading coefficient. Is it positive or is it negative? Let's just look at a few examples here. One we have in factored form. We have f of x equals negative 3x cubed times x minus 2 quantity squared times x plus 4. Well, that would give us a degree of 6. Right? We have 3 here, 2 here, and 1 there. And our leading coefficient is negative. So that's all we need to know to describe the behavior. If it's even and negative lead coefficient, this graph will fall in both directions. This next polynomial is a third degree, so that is a odd degree, and the lead coefficient is positive. So this behavior, we would fall to the left and rise to the right. So the lead coefficient test, we need to know, is the lead coefficient positive or negative, and is the degree even or odd? If we know each of those two pieces of information, we can describe the end behavior of any polynomial. Let's keep talking here about x-intercepts. So we're going to kind of fill in some blanks as we go here. To find the x-intercept, just like we would in other functions, we let y equal 0 and we solve. These solutions are also known as zeros. They're known as roots or solutions. And we'll see those used somewhat interchangeably. We can solve by factoring here. I'm just going to give you an example to demonstrate this here. We could write this polynomial, say x to the third plus 3x squared minus x minus 3. I can solve this by factoring. I'm going to set my whole equation equal to 0. I am going to factor by grouping. So I'm going to factor my left two terms and my right two terms. I'll be left with x plus 3 times x squared minus 1 equals 0, or x plus 3 times x plus 1 times x minus 1 equals 0. Just like we solved in our quadratics chapter, we're using the zero product property. So we would have x-intercepts at plus or minus 1 and at negative 3. The other way we can solve polynomials is through graphing. Not all polynomials are factorable, so we may have to enter into our y equals in our calculator and then find zeros. And that's where we use second calc and we find a 0 with our TI-84s. So those are going to be the two main ways that we'll solve these polynomials. Let's go ahead and try this example here, find the zeros or x-intercepts of this particular polynomial. I'm going to pause the video and work this one out. I suggest you guys do the same. Let's see how that went. So here you can see I set my equation equal to 0 and started by factoring a GCF. My GCF was negative x squared, and that left me with a quadratic times a quadratic. From there, I factored my quadratic trinomial into x minus 2 times x minus 2. And what I found is that I had two distinct solutions, right? Both 2 and 0. But because both of those solutions showed up more than once, I can see that 0 shows up twice because that x is squared, and then x minus 2 shows up in factored form twice. Both of my solutions have a multiplicity of 2. If we don't remember where that multiplicity idea comes from, the fundamental theorem of algebra tells us that the degree of a polynomial tells us what we need to know about the number of solutions. So in this case, the degree would be 4. Well, this fourth degree polynomial, we would expect to have 4 solutions. We only found 2 unique solutions, but each of these were double roots. In other words, they showed up in factored form twice, so we could say they have a multiplicity of 2. That brings us right into our next definition, our idea of multiplicity, and it is the number of times a factor repeats. Number of times a factor repeats. Now, when we have an even multiplicity, I'm going to make this a little bit more obvious to see what we're saying here. If we have even multiplicity, our graph will touch but not cross the x-axis. It will appear to bounce at that point. If we have an odd multiplicity, the graph will cross at that root. So it crosses the x-axis at the root. If the multiplicity, whether it's even or odd, is higher than 1, the graph will flatten at the root. As you can see here, these notes are pretty dense with vocabulary. So I think I'm going to pause here right at the end of page 1 and chop this video up into some smaller pieces. So you can move right along here to Polynomials Notes, Part 2. Thanks, guys.